Yo, time to wake 'em up!
Bonjour et bienvenue sur Discover 360. J'espère que cette chaîne vous plaira. Elle est consacrée à l'intelligence artificielle, au voyage et à la tech.
Yo, check the mic, 1, 2.
N'oubliez pas de souscrire. Bonne écoute.
Next cipher begin.
You know, most AI systems out there are built to do one thing, give you a best guess, even when they're totally unsure. And that's a huge problem, right? It leads to these silent, high-cost failures that can be an absolute disaster in the real world. But what if an AI could just stop and reliably say, I don't know? That one little phrase could literally change the game for safety and reliability. So today, we're going to dive into this amazing paper that gives us a practical blueprint for building exactly that.
So here's the plan. First up, we're going to look at why the simple true-false world that most AI lives in is basically a trap. Then, we'll get into the architecture and figure out the smartest place to build this I don't know gate. After that, we'll get into the really juicy part, the fundamental trade-off between risk and how much work the system can actually do. Then we'll roll up our sleeves and see how to actually build it. And finally, we'll look at all the ways this can go wrong and how to design a system that's truly tough.
Okay, so let's dive right in. What's the core problem here? Well, think about it. When an AI has to give you an answer, a confidently wrong answer looks exactly the same as a confidently right one. There's no signal. And that's when you get these invisible, really expensive screw-ups that can completely destroy trust and cause some serious damage.
And I love how the paper puts this. This is not some ivory tower debate about ternary logic. No, it's a practical economic problem. It's about dollars and cents and real-world consequences. Do we have a mechanism that knows when to go, when to stop, and when to ask for help? And, just as important, do we actually know what each of those choices is going to cost us? So, you might be thinking, is this a totally new idea? Well, not exactly. The groundwork for this was actually laid way back in the day with something called Chow's rule. It's basically the mathematical foundation for saying, I don't know. It gives you a formal, optimal way to decide when it's better to just refuse to answer, to abstain, instead of taking a gamble and maybe getting it wrong.
Okay, so we're sold on the idea. We need an AI that can say, I don't know. But now comes the big engineering headache. Where do you actually put this thing? Where in the whole complicated mess of a system do you build this gate that decides between true, false, or unknown?
Well, the paper breaks it down into 4 main spots. You could try to bake it right into the model itself during training. That can be super effective, but man, it's expensive and a real pain to iterate on. You could do it at the inference step, kind of looking over the model's shoulder at its raw outputs, or you could build it way up at the system governance level. But the paper points to a real sweet spot, the orchestration harness. In this diagram right here, it really nails the paper's #1 recommendation. Putting this logic in the orchestration harness, that's the traffic cop in your system that calls the AI, gives you the most bang for your buck. And look, for anyone who's actually building this stuff, this is a total game changer. Why? Because it means you don't have to retrain your massive, expensive model every single time you want to adjust your safety rules. It separates the brain from the safety harness, which is just a huge win. All right, so we know where to build the gate. But, and this is a big but, there's no free lunch here. When you give your system the ability to say, I don't know, you are forcing yourself to make a very deliberate, very important choice. And it all boils down to this tug of war between 2 key ideas, selective risk and coverage. Selective risk is your chance of being wrong on the times you actually decide to act. Coverage is just how often you act. It's a simple trade. If you want to slash the risk of your system doing something catastrophic, you have to accept that it's going to handle fewer things automatically. You're trading raw automation for reliable safety. So to get this balance right, your old friend accuracy just isn't going to cut it anymore. You need a whole new dashboard of metrics. You need to be tracking coverage and selective risk, plotting them against each other, and thinking about the actual cost of a wrong decision versus the cost of abstaining. And maybe the most important one, calibration. You got to ask, does the model's confidence actually mean anything in the real world? Okay, so we've got the why, we've got the where, and we know what numbers to watch. Now for the fun part. How do we actually build the thing? How do we go from theory to code? Okay, so one of the coolest tools for this is something called conformal prediction. Now, don't let the name scare you. It's actually a pretty simple idea. Instead of one single high-stakes answer, it gives you let's call it a bucket of possibilities. And here's the magic. It comes with a real statistical guarantee that, say, 95% of the time, the right answer is somewhere in that bucket. And if that bucket gets way too big or it's full of contradictory stuff, boom, that's your signal. That's when the system can confidently say, you know what, I'm not sure.
Operationally, this boils down to this really clean 4-step recipe. Step 1, get your answer from the model, along with the score of how likely it is to be right. Step 2, send that score to our new bouncer, the ternary gate, which uses some carefully chosen thresholds to make a call: true, false, or unknown. Step 3, if the call is unknown, you pass it off to a special handler. And step 4, that handler kicks off a specific action: ask a question, double-check a source, or page a human.
And what I absolutely love about this setup is how clean the separation is. You've got the gate on one side, its only job is to ask, are we sure enough? Yes or no. Then you've got the policy writer on the other side. Its job is to figure out, okay, we're not sure, now what? This separation of deciding from acting is just brilliant engineering. It makes the whole system so much easier to build, test, and maintain. Okay, but let's be real. This isn't magic. Building this kind of system introduces a whole new class of things that can go wrong. We have to be smart and think about these failure modes up front. And the paper calls them out loud and clear. You could have a system that's just too shy, it says, I don't know all the time, your users get annoyed and nothing gets done. Or the opposite, it's still too cocky and makes mistakes. And this one's wild. You could even have an AI agent that learns to cheat. It figures out it can just say, I don't know, to avoid getting penalized for a risky move. You could also just completely swamp your human operators. And my personal favorite, safety theater. It looks safe, it says the right words, but underneath, it's just as brittle as before. And that's exactly why, when the stakes are high, like with an autonomous system, you can't just have unknown pop up an error message. No, that unknown has to be a hardwired trigger. It needs to kick off a specific, pre-planned, safe-by-default action. That could be falling back to a simpler, dumber controller, pausing everything to ask for human approval, anything but just plowing ahead blindly. And all of this brings us back to one final, really provocative question. We are all obsessed with chasing that extra 0.1% of accuracy, pushing from 99 to 99.1. But is a 99% accurate AI really safer than one that's, say, 95% accurate, but it knows exactly when it's in that other 5% and can act accordingly? This paper makes a powerful case that we might be chasing the wrong goal. That kind of self-aware AI, well, that's not just better tech, that's an AI you can actually trust.